So this first lesson is going to look at some applications of vectors, in particular force and velocity, two of the more common applications. When you move an object, you're moving in a certain direction with a certain amount of force. That's an obvious example of a vector. Or if you're going somewhere at a certain velocity, you have a direction and you have a magnitude of size, we call it your speed. Again, a pretty common application of vectors. So we can go through basically a series of examples for this lesson. We have Buffy and Chloe, and they're pushing a crate across the floor. So if we think of this as our crate here, Buffy's pushing with a force of 50 newtons towards the west, so she's pushing this way. That's 50 newtons. And we got Chloe pushing south. They're not very smart here. They're pushing in opposite directions, or not in tandem. They're pushing just different directions. We want to figure out the resultant force. How much force is actually being applied to this crate? Now we know from past experience that when things are tail to tail, we can complete the parallelogram. Okay, so we put the other one down here and the other one over here. And then if we do tail to tip, the resultant force would go diagonally south-west. I want to figure out the resultant force. So the nice thing about this is we've got these two cardinal directions. We know we can use right angle ideas. So resultant will be the square root of 50 squared plus 35 squared. And we can move the 35 over here. We got a Pythagoras question. Square root of those two things together comes out to 61.03 newtons. And remember, with forces, we need to have a magnitude, a size, and we also need a direction. When we talk about directions, we talk about it in relation to one of the two forces. So in this case, we'll talk about maybe relation to 50 newtons. If we think of this as, again, a right angle triangle, based on where x is, this would be my opposite. This would be my adjacent. I can say the tan of x, just using SOHCAHTOA, is 35 over 50. Or if I do the inverse tan of that, I will get, make sure I calculate in degrees, approximately 35 degrees, or 34.99 if you want to be exact. So the resultant force would be 61.03 newtons at a 35 degree angle to the 50 Newton force. And we usually describe our angles in real world kind of examples like this in relation to one of the two forces, as I was saying. Okay, that's the most basic kind of question. Our nice right angled cardinal direction, use Pythagoras and SOHCAHTOA type question. Okay. Other times, we know the resultant. And the thing we want to figure out might be, well, what forces were used to create that? In the real world, we often think of our horizontal force and our vertical force as the two components that were used to create the resultant force. If I lift an object, well, part of it's lifting it off the ground, but part of it's also moving forward. Those two things get together to make the horizontal and vertical components up. Okay, so if we look at the second example here, we're looking at a lawnmower. We have a gardener pushing that lawnmower at a force of 250 newtons along the handle. Okay, so if this is my handle, the mower would be down here, and the 250 newtons is going that way. The handle is inclined at an angle of 60 degrees to the ground. So if I think of this as my ground down here, this would be 60 degrees. And I want to know how much force is actually pushing the mower forward. So again, if I think of this as a triangle, it'd be a right triangle, we call this a horizontal force, FH. And that's really what I'm looking for in part A here. Nice news again is, well, it's the right angle triangle. SOHCAHTOA will come in handy. Okay, based on the 60, this is my adjacent and my hypotenuse. So I'm using cos. Cos 60 equals FH, the horizontal force, over 250. We can cross multiply that, 250 times the cos of 60, and put that into our calculators, and we end up with 125 newtons. That's how much force is actually pushing that mower forward. Okay. If you look at part B is asking us for the magnitude that tends to push the mower into the ground. Well, that would be the vertical force. And even though obviously when we're pushing a lawnmower, we're not trying to push in the ground, some of our force is helping to keep the mower on the ground. We are pushing down to some degree. Again, SOHCAHTOA, so sine 60 this time, since we have the opposite. But everything else is exactly the same process. We can cross multiply again, and our vertical force will turn out to be 216.51 newtons. So by pushing at an angle of 60 degrees, which is a pretty steep angle, we actually have more force pushing the mower into the ground than we do have the mower going forward. Right? Thinking about that in part C here, how would the person pushing the mower be affected if the angle is increased? Well, the steeper the angle, the more force that's actually being extended down. We're exerting more force into pushing the mower towards the ground. Logically thinking, the best objective if we want to mow the grass is to keep that angle really small, so our force, the 250 newtons that we can push with, actually pushes the mower forward rather than just keeping it on the ground. All right, so let's take a look at another idea. Sometimes you have these forces that are acting on this object, and there might be more than one of them. We had the Chloe and Buffy example there, right? There are two people pushing in the same direction. Well, every time we do that, we create a resultant. Sometimes we want to know the force that could act against that resultant. What if I want to prevent Chloe and Buffy from being able to push that crate somewhere? What would I have to do as a single person to counteract that? Okay? That single force that counteracts other forces is called the equilibriant. Okay? It keeps the object in equilibrium. If we go back to Chloe and Buffy, go back to that first page there of examples, okay, the resultant was 61.03 newtons at a 35-degree angle to the 50 Newton force. To counteract that, I would have to do the exact same thing, but in the exact opposite direction. So I would need to counteract that with a 61.03 Newton force at an angle. And here's the one part you have to think about a little bit. And we had the angle here before was about 35 degrees. It was going this way. So if I want to counteract that, I have to figure out, well, what if I go that way then? How much is this piece in here? Okay, so to figure that out, we can take 180, because the straight line makes 180, subtract the 35. So if we took 61.03 newtons and we acted at an angle of 155 degrees to the 50 Newton force, okay, remember this was 50 newtons here, right? We could totally counteract anything that Chloe and Buffy could do because we're acting in the exact opposite direction at the exact same amount, and that crate wouldn't move anywhere. And again, we call this the equilibriant, the one force that counteracts other forces. So an example of that is example number 3. We've got two forces. One's 20 newtons, one's 30 newtons, and they act at 120 to one another. And our objective when we talk about things acting one another means tail to tail. It's always tail to tail. Okay. I want to know the magnitude of the equilibriant in the angle makes with the 30 Newton force. So to figure that out, I kind of need to know the resultant and then figure out its opposite. So let's take a look at this picture here. We've got a 20 Newton force, and we've got a 30 Newton force. And we know they're making an angle of 120 with one another. And because they're tail to tail, we can complete the parallelogram. We got that one. We got that one. So our resultant would look like this. The equilibriant, the thing that balances that out, would be the same vector, just in the opposite side. Okay. The question asks us to figure out the magnitude of this. Call this E. Well, the magnitude of E is the same as the magnitude of R. And it also asks us to figure out the angle makes with the 30 Newton force. So if I can figure out this angle, then I can figure out that angle because together they make 180 degrees. So if I want to figure out the magnitude of an equilibrium, I got to think about the resultant. Going back to our C pattern, if I've got 120 down in the bottom left corner here, that means the other corner has to be a 60. Because together 120 and 60 makes 180. I know this is a 30 Newton force. I just translated the vector, which means I can use the cosine law. So I got r squared equals 20 squared plus 30 squared minus 2 times 20 times 30 times the cos of the angle between them. That's 60. Okay. We can put that all in our calculator, make sure we square root it at the end, and I got 26.5 newtons. Okay. If I want to find the angle that the resultant makes with the 30-degree Newton force, remembering, keeping in the back of our minds, I need that to figure out the angle for the equilibriant. I need to use the sine law. Okay, so what can I match up? Well, I know that 60, remember this is 60 up here also, will match with r. We just figured that out. 26.5. The sine of x will match with, that's 20. It's the same vector at the top as it is the bottom. And I can solve this by cross multiplying and then taking an inverse. If I do that, I end up with like 20 sine 60 over 26.5 equals sine x. And I put that on my calculator, take the inverse of it, and x will come out to 78.2 degrees. Okay, that's the angle of the resultant. Everything I've done so far is the resultant. If I want to figure out the equilibriant is, well, it's the same size, same magnitude. So 26.5, sorry, not 4. 26.5 newtons at an angle of, and we're trying to get y right here, right? This angle right here. And so y equals 180 minus x. We said x is 78.2, so 101.8 to the 30 Newton force. And generally the questions will tell you which force you're dealing with. If you want it against the 20 or against the 30. It doesn't really make a difference. It's just which angle you find in the first place. Okay, and that's how we find an equilibriant.